Hi everyone, my name is Supreeth and I'm a graduate student at University of Wyoming and a student assistant at NCAR. My poster is about implementation of dynamical core component of an MPAS atmospheric model using OpenACC directive. What is MPAS? MPAS stands for Model for Prediction Across Scales. It generates the Earth system simulation components which are used in weather and climate research. So MPAS code spends most of its time in executing the dynamical core, which solves the 3D non-hydrostatic equation of motion for atmosphere. So the current version of MPAS uses OpenMP plus MPI to run in parallel. So our main goal for this project is to port the entire code of MPAS to work on GPU or using OpenACC directives. So as a first step, we profiled our code using gprof. So profiling shows that we have three major time-consuming functions. So first one is ATM underscore advanced acoustic step, which corresponds up to 31% of the time. And we have ATM underscore compute underscore time 10, which corresponds up to 25% of the time. As a preliminary step, we took ATM underscore compute underscore time 10 to optimize. This is mainly because it is called less number of times and the percentage of time is small. So first question which comes to mind is why we chose OpenACC. We chose OpenACC mainly because of two aspects. One is portability, other one is performance. So we want to write a single piece of code which runs on multiple architecture as well as device. And also we want to get a good performance out of it. So as performance optimization, we have done two levels of optimization. The first one is loop fusion. When we have two loops which are independent to one another, we can combine two loops into a single loop. So this is shown in the pseudocode. We are calculating A and X in two separate loops, but the iteration count is same in both the loops. So we are able to merge it to a single loop. So this will save some instruction as well as time to launch another kernel. As a second step, we did the loop breakdown. So dependency between the two loops can make the code run in a sequential manner. So we want the code to be as independent as possible. So to achieve the same, we did the loop breakdown. That is, if you see the pseudocode, we have W of k dependent variable. So we promoted the W of k into 2 dimension so that we will have two independent do loops. So we measured all our performance on Yellowstone Caldera node, which is 2 socket 8 core Sandy Bridge node along with a K20X. So we achieved a maximum speed up of 4.x and the code scales very good up to 8 cores, and thereafter the scalability is low. This is mainly because of the bottleneck introduced by the QPI memory bandwidth. We can increase this scalability by better placing the thread and data on the node. So we haven't investigated the idea of threading because the OpenACC cannot currently exploit this capability. So without changing any code, we are able to run the code on GPU, and we are able to achieve a speed up of 8x. This is because of the massive parallel architecture of the GPU. One thing to note here is we are not including the data transfer time. This is mainly because we are planning to port the entire code of MPAS to the GPU so that data transfer will mainly become input-output communication. So to conclude my video, we have finished the preliminary OpenACC implementation of the kernel, and also we are able to get a speed up of 4.5x on the CPU and 8x on the GPU. Thank you.